This video is about layer normalization and batch normalization, and these are two very key techniques in modern machine learning approaches that help us train models faster and allows us to train deeper neural networks. So we will be limiting our discussion to a feed-forward neural network just because of its simplicity, but the same discussion applies to other types of architecture, and the framework remains exactly the same. So let's consider the following network. We have an input X, which is one-dimensional, again for simplicity, and we have two hidden layers shown here in gray and green, and then you have an output which is also one-dimensional in this case. So let's say you train this network, and you train it by sampling the input from some training distribution, which is shown here in red. And when you deploy this model in a testing situation, you realize that the test inputs now come from this purple distribution. So there has been a distribution shift post deployment. Because of this distribution shift, the model might not perform as good as it performed during training or validation. So maybe during training you saw an error of 98%, but during testing you realize, okay, the accuracy dropped to 80%. So distribution shift makes it difficult for the model to learn the relation between the input and the output pair. Now, to handle this type of distribution shift, it is recommended that you collect input samples that are representative of the testing distribution and so on. But in the following slides, I'll present to you how such a distribution shift is also happening internally inside the model. And when it happens internally, it makes training difficult or indeed slower. And slow training is not desirable if you have a very deep neural network, because you'll end up spending a lot of computational resources to get reasonable accuracy. So let's try to understand what I mean by an internal distribution shift, and this is summarized as follows. So let's introduce some notations. The weights from the first layer I denoted with W1, the weights from the second layer I denoted with W2, and I'm going to hide the left hand side of this network. So let's view the right hand side of the network as a standalone neural network, and this receives an input from the left, and this input would be the output of the left hand side of our neural network. Okay, we will be denoting this input with the variable h, and this variable h is obviously a function of these weights. So these weights that you compute in the first layer, they control how much the input changes. So let's try to understand how the distribution for this input h can change as you continue with training, right? So when you'll do your first epoch, you'll get a certain set of weights, W1, and this would change the input H1. And if you were to plot the distribution, it might look something like this. Now in the next epoch, the weights will change again. So your distribution might look like the purple one, and it might shift even further as you continue with your training regime. So there is this internal distribution shift happening inside the model, and this makes it quite difficult for the right-hand side part of the network to perform learning. So there's a distribution shift for this part of the network, and this is what makes learning slow. So controlling this distribution shift is what we try to achieve with both batch normalization and layer normalization. So let's first start with batch normalization, then we will discuss what are the drawbacks of batch normalization, and eventually we can close our discussion with solving these drawbacks using layer normalization. So batch normalization works as follows. We represent the weights of a network with W. So W can represent this weight, or it could represent any other weight. And when you're training this neural network, you'll have gradient descent updates. You take derivative of the loss function, which is denoted here with L. So the loss function L will depend on the input X, and you take the derivative with respect to the weight that you have. You move in the opposite direction of the gradient, and that's why you see the minus. Then you have some learning rate represented by alpha, and you perform the following update for your weight W. So one can conclude from this expression that W actually depends on the input. So W is a function of the input. If you change the input, then the weight changes because of these gradient descent updates. I'm not talking about the testing regime. In the testing, when you've deployed the model, when you're just testing the model, the weights are frozen. We're talking about the training epochs where the weights can change with the input. So once we make this observation, normalizing W is very straightforward. So one way to normalize this is as follows. So you subtract the average, and you take the average with respect to the distribution of X, and that's why you see the subscript X. So when you subtract the mean, this means the mean of W bar would be 0, right? So you subtract the mean, you made the mean 0, and then you divide it by the standard deviation, which is the square root of the variance. And this ensures that the standard deviation of W bar is 1, right? So you constrain the mean to be 0 and you constrain the standard deviation to be 1, and that's one way to normalize a random variable. Okay, so if you were to just plot the distribution of W and W bar, it might look something like this, just for the sake of example. So the unnormalized random variable W will have a mean which is non-zero and will have a standard deviation which is also different from 1. But when you normalize it, you'll see that the distribution is kind of centered around 0, and it will not have very thick tails because the standard deviation has been constrained to 1, right? So that's good because we've constrained the distribution in some way. But then the question is, how do we compute the mean and the variance? We don't know the distribution for X, and that's why a direct computation of this mean and variance is not possible. So to compute these mean and variances, we proceed as follows. So we realize firstly that during training, we will be splitting our training data set into different batches, and I'm denoting these batches with these square boxes, and if you take a union of all these batches, you get the entire training data set. Okay, so D1 is our first batch, DM is our last batch, and so on. So when you divide this training data set into batches, you can use each of these batches to perform an approximation for the mean and variance that we had in the previous slide. So how do you approximate the mean? We take an average of the different weights that we observed over the different samples in the batch site. So N would be the number of samples in your batch DI. And you do exactly the same computation for the variance. So for the variance also, you take the mean. But this time you subtract the values from the mean, you square them up, and then you take the average. So that's a standard Monte Carlo approximation to a mean and variance. And once we have these approximations, then normalizing is very straightforward. You just normalize with the approximations, right? So you subtract by the mean approximation and you divide it by the standard deviation approximation. Now, I have been quite sneaky here. I introduced 2 new parameters without really introducing them. So let's get into the details of these. So I introduced 2 parameters, gamma and beta. And these 2 parameters are trainable. And just like the weights, we will update them using the gradient descent step that I discussed in the previous slide. And what these parameters are allowing us to do is to give the model the freedom to adjust the mean and the variance accordingly. Our goal was to input a distribution or to input a variable which has 0 mean and 1 standard deviation. Okay, and that's what we did using this scaled expression that we have. Now we are letting the model to choose whatever mean and variance it wants with the help of the trainable parameters gamma and beta. And now the question is, how do you actually perform this normalization during testing? Because remember, also during testing, we need to perform this normalization. This normalization cannot just be switched off when we are doing testing. Now in testing, the difficulty is that we don't have, or we might not have batched data. We might want to do online inference where we have data coming in, one test sample coming in, and this one test sample then needs to be normalized. Obviously, we cannot apply this approach directly because taking just the mean and the variance using one sample would be highly inaccurate. You'll have simply too much noise. So there is no batch data during testing. So how do you deal with this? The solution is very simple. So while you're looping over the different batches that we had in the training data set, you keep a moving average of what mean and variances you've seen, right? So as you iterate over these batches, you will compute some mean and variance for the batch D1 using these 2 expressions. Then you will compute some mean and variance for the batch D2, and then you will take an average of these 2, or you'll take a weighted average using the exponential averaging approach. So the crux is that you keep some moving average of the different mean and variances you're computing for different batches, and you will use this moving average during testing. So during testing, you will not at all be computing any mean and variances. As for gamma and beta, as we discussed earlier, these are trainable parameters. So once training is complete, they are frozen. So testing, we don't have to worry about choosing gamma and beta during testing. So now we are ready to discuss 2 key drawbacks of batch normalization. And the first one is, I think, quite obvious. So if you don't have a big enough batch size, right, then the approximation for the mean and variance that we had will be too noisy. It won't be reliable. And this is a drawback. So when you don't have a good approximation of the mean and variance, your normalization will not work as desired. And you might think, why not Why not just take big batch sizes? Now, sometimes that's simply not possible. Now, think about distributed training, for instance. I mean, so you're training on multiple GPUs. You've distributed your data set over multiple GPUs. So it might simply not be possible to give big batches of data. The second drawback is more related to large language models and natural language processing, and this has to do something with time series data. So if your input now changes with time, right? So if you have different distribution for each time step, you need to compute a different mean and variance for each different time step. And this is what I'm denoting here with the subscript t. So for t equal to 0, you'll compute a different mean and variance. For t equal to 1, you might compute a different mean and variance, and so on. Okay, and then during testing, you will use these same mean and variances to perform normalization for the test data. If you remember from a previous discussion, we're not doing any mean and variance computation during testing. We're using the averages that we computed during training to perform normalization during testing. Okay, so what happens as a result is as follows. So let's say during training, you only saw sequences with two timestamps. So you had timestamp t equal to 0 and t equal to 1, and you had no other timestamp whatsoever during training. So that means you will only have mean and variances for t equal to 0 and t equal to 1. You will not have any variance for a timestamp more than t equal to 1. Okay, but during testing, your sequence length increases. So instead of having only two timestamps, you have a third one, which is t equal to 2. So what happens now is that you won't be able to perform any normalization for t equal to 2 timestamp because you didn't have any data corresponding to the mean and variance. So that's a big drawback, right? You cannot perform any normalization if your timestamp is greater than 1. This means you're limited to only those testing sequences which have timestamps less than equal to 1. This problem continues for large language models. So here is an example. So let's say you have 3 sequences in your training data set. Okay, now you can allocate a timestamp to each word in the sequence. So the first word could be t equal to 0, the second word could be t equal to 1, the third word could be t equal to 2. And you cannot have testing inputs which have more than 3 words because you won't be able to normalize the fourth word. You simply won't have the data as we discussed here. You simply won't have the mean and variance values to perform normalization for your fourth word. So that's greatly limiting. You're limited to testing sequences which are less than or at least or equal to the training data set. Now let's look at layer normalization. So in layer normalization, we're just going to focus on one of the layers of our neural network. The formulation remains exactly the same for the others, so we don't need to worry about that. And with W, let's denote a random variable that represents our weight. So this W, if you remember from the previous discussion in batch normalization, W was a random variable, but it denoted the weight of a particular neuron. In this case, W is a random variable that denotes the weight of our entire layer and the weights of each particular neurons. So W3 is the weight of the third neuron, W2 is the weight of the second one, W1 is the weight of the first neuron. These are realizations of the random variable W. Okay, so there's a difference in interpretation here. Now, as soon as you view these values as realizations of a random variable W, normalization is just straightforward. So you compute the mean. How do you compute the mean? You take the average of these realizations. And how do you compute the standard deviation? You just compute the mean of the different deviations. So then the normalization is exactly the same as what we did earlier. So we have this variable W hat or W bar that we defined earlier. So we subtract the mean, we divide it by the standard deviation. This ensures that the mean is 0 and the standard deviation is 1. And then we allow the model to find its own mean and standard deviation, and that's why we introduce the variables gamma and beta. So both of these parameters are trainable. Now I totally understand that the foundations of layer normalization are a bit hand wavy, right? A bit sketchy. So for batch normalization, it was quite clear. Every weight is a function of the input, and that results in a standard normalization technique. Here, it's not very obvious why these different weight values are realizations of a random variable W. But despite of there being a shaky foundation, it works very well in practice, and particularly for large language models, right? So all the latest large language models, they use layer normalization. None of them use batch normalization. So here is a plot from the paper that I listed in the description. I would really recommend reading that paper. That's the original paper on layer normalization. And what the authors are trying to study is how quickly you can train a model using the different normalization techniques. So here you can see 4 different curves. The blue one corresponds to an unnormalized model. So basically, you don't do any normalization whatsoever, and you just learn. You just let the model learn. On the y-axis, you have the validation error. On the x-axis, you have the number of epochs you took. So basically, as you go from left to right along the x-axis, you're going further. You're proceeding with your training regime. Okay, and as we discussed earlier, the training is slow. One of the main reasons for this is the internal distribution shifts that we talked about. Now you can improve the speed of training substantially if you introduce normalization, right? So these two curves, they represent batch normalization approaches, and you can see you reach an asymptotic validation error much faster than the unnormalized approach. And finally, we have layer normalization, which is shown here in blue, and layer normalization has the fastest conversion rate in this case. So the error drops, the validation error drops very quickly as you continue with your learning. So this would mean that, with layer normalization, at the expense of introducing a few additional parameters, you have saved so much computational cost. You need almost 5 times more iterations to reach the same validation error. So the key takeaway here is you can speed up learning with both normalization approaches, and you can really gain a lot in terms of the conversion speed as compared to a plain vanilla network, as compared to a plain network that does not have any normalization whatsoever. So this brings us to the end of our discussion, and there's just one thing I would like to point out in the end, which was not that obvious from the last slide. So the key difference between layer versus batch normalization when it comes to the implementation of these two approaches is that batch normalization computes mean and standard deviations column wise, and layer normalization operates on a row level. So let me just discuss what this means. Let's say we have some input X with 3 input features, right? So age could be 1, height could be 1, postal code could be 1. So the column dimension represents the feature dimension, right? And these different features are stacked on top of each other, and this results in the batch dimension, which is along the different rows of this input matrix X. Okay? So what batch normalization is doing is that it's computing the standard deviation and mean for each of the features separately. So age will get its own mean and variance, height will get its own mean and variance, and postal code will get its own mean and variance, and you will normalize each of these features separately using these mean and variances. And that's what I've summarized here. So you're computing mean and variance along the batch dimension for each of the features separately. Okay, and that's where the problem of not having enough batch, not having a big enough batch dimension comes in. So if you don't have a large number of rows, then your approximations for mean and variance won't be that accurate, and normalization won't work as desired. Now, layer normalization, on the other hand, is combining features, so it's acting along the row level, and that's what the last image summarizes. So along each row, you compute the mean and the variance, and using these values, you normalize each row separately, and that's why layer normalization can also work with just one row, which is not the case with batch normalization. So in batch normalization, if you just had one row, your approximation would be too noisy and it won't work. But there's something unusual about layer normalization, and that's the combination of features. So you're kind of combining feature information, right? So you're combining age, height, and postcode together, and you're computing the mean together. Although these values that I've indicated here are just for the sake of example. In a real world machine learning problem, you would have normalized them and probably brought all these values between 0 and 1. But still, the relevance remains the same, that these would be normalized age values, normalized height values, and normalized postcode values. And you will be combining these values to compute the average. There is a feature interaction which is not very natural. But despite of that, as we discussed earlier, it works very well in practice. So that wraps up my discussion around batch and layer normalization. In the following videos, I'll be discussing more interesting concepts around machine learning.